a Pauli, exponentiate it, and evolve these qubits under that, right? So it tells us what phase and what the Paulis are if we click on it. So this looks like what we expected, and if we wanted to explicitly decompose it to get it in terms of basic gates, we can run this decompose boxes transformation and look at that, and we get a load of C0s and RZ gates. And this is in ZX form. If I click this, it goes into normal circuit form. Okay, and we're going to proceed very similarly for the mixer, but the mixer is a much simpler Hamiltonian. I just put an X on every qubit to construct the operator, so I can construct the whole operator in one line and use the same principle to look at that. In this case, the decomposer thinks it should decompose to RZs and Hadamards, but each of these is actually just an Rx of the same amount. A Hadamard RZ Hadamard is just an Rx. Okay. Why? It's just an example. So, it could be any random value. Yeah.
So you start with any value?
You start with any value, exactly. Yeah.
That's what's called the ansatz.
Right. So we're about to define the ansatz, exactly, by putting these pieces together. So our initial circuit for QAOA is just a Hadamard on every qubit. So this function does that. If we give it a number of qubits, it initializes it and then applies a Hadamard to each of those and gives you that. So we can call that the superposition circuit because it prepares a uniform superposition over all basis states. And look at that. Not very interesting, just Hadamards. And to make the full circuit, this function is going to put all these pieces together. So we prepare our initial circuit, which is just a superposition. And then based on the angles we gave it, so if we've given it a list of mixer angles and a list of problem angle, cost angles, it applies one layer of the evolving under the cost Hamiltonian and one layer of evolving under the mixer Hamiltonian. So we're just putting the pieces together. So let's define that function. So that prepares our circuit. Now, to get any useful information out of it, we have to do measurements. So we need to think about what are the measurements we need to do on these qubits to get the information we need. And specifically, what we're trying to measure is, for a given state, how well does it solve the problem, i.e., what is, if we measure the value of the cost Hamiltonian on the state, what do we get?
In this example, we're doing just one step of the evolution, just one layer.
So the number of layers depends on the length of these lists you give it. So these lists need to be the same length, and if you give it length 1, it'll apply 1 layer. If you give it length n, it'll apply n layers.
So you decide how many?
Yes, that's an experimental toggle that you can use.
On how many nodes?
It doesn't depend on how many nodes, exactly. Yeah, it's a control onto how exact you want the algorithm to be. So in theory, as n tends higher, the algorithm becomes less and less approximate. Okay, so the generating measurement circuit works by, so by default, if you measure a qubit, you're doing a Z-basis measurement. If you want to measure any other Pauli, you need to do a basis transformation, so rotate that qubit into a different basis, and then do a Z measurement. So this function handles that logic for you. This is actually a copy of another utility function that is already in PyTicket, but to just look at what it's doing, we give it the Hamiltonian we want to measure, and so if we have, this requires a bit of scrolling, if we have a Hamiltonian like this one, we can see this is a sum over 3 terms, but in any one measurement, we can only measure one term. So, because these all each term acts on all the qubits, right? So if I want to measure ZZI, what I can do is measure qubits 1 and 2, and find the expectation value over that. And then if I had, say, this operator was IXX rather than ZIZ, I would have to do a basis transform to measure IXX over a different set of circuits, and then sum all my expectation values together to get the overall results. So this handles that for you as well. So given the initial state you started with, which is your preparation circuit, it prepares a list of circuits for measuring all the terms in your Hamiltonian. So for each term in your Hamiltonian, we append the measurement basis transformation gates required, and then append the measurements, record the answer to a bit, and then add that circuit to the list. So in general, if you use this function, you'll get out, if you put in your preparation circuit and your Hamiltonian, you will get out as many circuits as there are terms in your Hamiltonian. Okay, and then, so each of those circuits, if you measure them, will give you just the expectation value of that term, but to measure the value of the whole overall Hamiltonian, we need to do the multiplication by the coefficient and then do the sum. Well, it won't even give you the expectation value, it'll just give you a load of samples, right? Like I measured 001 or 100, whatever. You need to calculate the expectation value, multiply that by the coefficients, and then calculate the sum. So that's what we do in this function. So what we're doing is we give it a list of results, one corresponding to each term. We also give it all the circuits we used, so we know which measurement results to extract, and we give it the operator we're trying to measure. So what it does is it goes through for each result and each circuit corresponding to that result. We ask for the counts of each basis state from that circuit by providing the bits that those measurements are recorded onto. And then we use this expectation from counts function to calculate the expectation value. And then we just organize the results here and store it. And then finally, to calculate the actual energy, we take that result, multiply it by the coefficient, and add it to our ongoing estimate. And this will return the overall estimated energy. Okay, so now we should have all the pieces we need to actually set up our experiment. So here we're going to set up the QAOA instance function. And we're going to try and keep this flexible so we can change our minds about which backend or device or compilation we're using later. So it takes a backend, the target that you're going to run the circuits on, and it takes a function that acts as a compilation pass that'll take a circuit and do something to it. And it takes the your guess for the mixer angles and the cost angles as an umpire array in this case, but it could just be a list of floats. And it also takes the number of shots you want to run. So each time you run a circuit, we need to run it a number of times to get statistics. So here we have a parameter for how many times we want to run each circuit. And at the end of it, it will return you the actual energy. So we start by getting our max cut circuit from our function earlier. And then we prepare the cost Hamiltonian. We get all of the circuits we need to measure. And then we compile each of those using the provided compiler pass. And then we use this process circuits function. So this is the primary way with the given backend. Every backend has a process circuits function. You can give it a list of circuits and the number of shots you want to run. Or if it's a state vector simulator, you don't need shots. It just simulates the whole state. And that acts as a submission. And it returns a list of handles that you can later use to go and retrieve. So I could potentially do a load of, if I was using a Continuum remote backend, I could do a process circuits here, and then take the handles, record them somewhere, dump them to file, come back the next day, load the handles, and then retrieve all the results once the machine is done with it. But in this case, we're going to be using simulators or emulators, so we expect the results to be available quite quickly, so we just get the results. We ask for the results immediately. And if they're not available, this function will wait for all the circuits to complete before retrieving the results. And then we can use our estimated energy function to get the energy. Okay. So this might be a slightly unfair question, but given the possible terms in our cost Hamiltonian, has anyone here thought of a simplification we can make to actually measure it, rather than the approach I've detailed so far? No? Okay, that's fair enough. I will tell you. I said earlier that in general, if you have a set of terms, you'll have to measure a circuit per term. And that means if you have n terms, you have to run n circuits, n number of shots times. So that's n times n number of shots. So the number of terms you have is actually quite prohibitive. And in certain, this is a big problem in chemistry, where for certain Hamiltonians, your problem, your number of terms scales then to the 4, which becomes really prohibitive. But in our case, our terms are all made up of z's or i's. And so we can actually measure all of these together. If we just measure all the qubits, then if we just ignore the third one and perform this calculation, we get ZZ. Or in this case, if we ignore the middle one and do the rest, we get this term. So in fact, for our Hamiltonian, by just measuring one circuit, we can get all the terms. And in general, if you have two terms that commute, you can measure those together. So there is some tooling in PyTicket as well. So for a general Hamiltonian, it will partition the terms into commuting sets and produce measurement circuits from that by rewriting the circuits to try and minimize the number of circuits you actually have to run. But in this case, we can do that by hand because it's so easy. And so we're going to define a much simpler instance. Okay, so in this case, we can define a new max energy function that takes our edges as a list and the results. And we can use the get distribution function to get the actual distribution of results, i.e. This state was measured with this probability as a dictionary. So 001 was measured 50% of the time, and 100 was measured the other 50% of the time, or something like that. And so for each edge, all we have to do is we take the state that was measured. So say it was 01. So there should only ever be two terms because we only ever measure 2 qubits per term. And if we just do the XOR between those, we get our cost function. Hopefully you can see that the xi times 1 minus xj is, you can redefine that using the XOR function. And then we just times that by the probability to get the weighting and sum the whole thing, and that's your energy. So we can use our cost function more directly here. So in our simplified instance, we get our prep circuit. We just measure everything. We apply the compilation circuit to that. We run just that circuit, and we use our max cut energy function to get the energy. So if you've got n terms, i.e. n edges, instead of running, we've just scaled down our problem in runtime by n. So I'm going to keep using the simple one for the rest of this, but if you go back to this, the more detailed one is quite useful for exploring how to do this kind of stuff in general. Okay.
So basically you eliminated the identity?
No, I eliminated running a different circuit per term. I'm running one circuit, and that will give me all the terms. Because all the terms in our problem Hamiltonian commute. Okay. So what we're left with then is we have a way of preparing our state, and we have a way of measuring it. Sorry, actually, the timing is incorrect. It's quarter to 4, and we finish at 48. Okay, cool. All right, we have a way of preparing our state, and we have a way of measuring our cost Hamiltonian out. So what we want to do is set our parameters in such a way that our cost Hamiltonian measurement is as high as possible. Now, you could imagine a number of ways of doing this. For the purposes of keeping this scalable and repeatable and so on, we're going to take a very naive, stupid approach, which is just try a set number of random values for the parameters and just pick the best one. This is terrible, but it's instructive. So that's all that's happening here. We set the number of iterations we want to, the number of attempts we want to make, the number of shots we want to do, and I'm seeding the simulator here so that the experiment is repeatable. But otherwise, we just randomly sample some angles. We set up our simple instance with that, And if the energy we just measured is higher than the one we measured before, we update it and keep track of it. So let's define that. If you think you can do better than this stupid way of finding it, try exercise 3. Okay, and then this function is, I mean, I won't spend too long on it, but essentially it's just once you've found the best angles, find out what the best state is that corresponds to by preparing the state based on those angles. Okay, so let's use the air backend from Qiskit, which is the air simulator. It's noiseless, it's a perfect simulator, and we're just going to use that backend, and we're going to use the default compilation paths for that backend that Callum mentioned earlier to run our calculation. And we are going to ask for it to plot the results at the end of it. So we'll define our backend. Yeah. So there will be a degenerate set of states that are optimal for the max cut problem, and each of those will be encoded by a different set of parameters. If your circuit is able to explore the full space, right? And we, in general, we need infinite n to explore the full space.
So the parameters actually encode the solutions.
Exactly, right. And so in an ideal case, you'd find the parameters that encode the exact solution. But our hope is that we get somewhere close. Yeah. Right, so if we now run this first one should be pretty fast. It looks like we started out at an energy of about 3, but we've gone up to 4.9. It should hopefully, there'll be a few of these where it's running. They are good times to ask questions. This one's done now. Right, so what we're plotting here, it's told us that the highest energy it found was 4.94, and these are the angles it found that it corresponds to. And then what it's done for us is plot for those angles, the probability of the basis states. So, and because we know what the correct ones are, we've colored the correct states in green. And so in this case, we see that our correct states are there with high probability, but there is still a number of other states. And this is a noiseless simulator, so this isn't due to noise. It's just because our preparation isn't exact. It's an approximate algorithm. And so there are a number of things we can use to make this better. We could do more iterations to try more values. We can use more shots to get rid of sampling error. We can use more layers in our preparation circuit, this kind of thing. Okay, but what happens if we actually use a noisy simulator? Is anyone coding along right now? Hands up, just you. If you have an IBM-Q account that you want to use for this, sorry, you're trying it now? Yeah. Then you can set it here using the set IBM-Q function. Your API token, hub project, whatever. If you have those, you can put those in, and then your account will be used for this emulator section. For everyone else, I'm just going to be using my account, so I won't be touching this. The reason we need this is because we're going to try and emulate a real device, in this case, the Guadalupe device, and we use this IBM-Q emulator backend from PyTicket. And the idea behind the emulator backend is it tries to simulate the connectivity constraints, the gate set, and the noisy behavior of the device, and such that if I just get rid of emulator in the middle of it, I can use the real device. So it lets you debug and test with an emulator, and then immediately switch to the real device if you want to, which we may do later on today. Yes. This will take a little second while it talks to IBM and asks it for all the current calibration information about Guadalupe. It's got it, and now we can just swap out the backend. Instead of using the simulator before, we use this emulator and run it. This is doing noisy simulation, which is quite costly, so this will run slower. And while that runs, I will look around for any, yeah?
What should we put in the hub group project parameters?
Right, so if you have an IBM-Q account, which you do, you have one of the open ones, just the public ones.
Yeah, I think I signed up with the email of
Right. So you just need to change, you can ignore the rest, and into your IBM-Q API token, you put in your API token from the IBM website.
What about the other?
So those are only if you are like an IBM partner and you have like a university account or something like that.
I mean, I've created the thing that they can use where they have additional access to the
Oh, they do? Okay.
devices. It's almost every boot device, and especially between 5 and 7, they use that thing where they're
Okay, so that should say which hub group and
yes,
project it is?
yes. But I mean, for now, they can also use
Right.
one.
Yeah. So if you have that information from Elisa, then the hub group and project names should be in there.
So, I don't know. I send it to you, it's like, the hub is,
We got that information.
oh, you received an email.
Yeah, we got it on the email, but the ID token you need to find on the web page.
Yeah. Yeah, your API token is, each one is individual, and so like it's not good practice to put it actually in the notebook or share it, so I don't know, get rid of it afterwards or do it in a terminal like this one. And oh no, I've shown my API key. Everyone forget you saw that.
Wrote it down already.
Yeah.
That's on stream actually.
Sorry?
That's on stream actually.
It's on stream. It doesn't matter, I'll just change it. I just need to hit refresh on IBM and they change it, I think. If anyone else makes the same mistake I do, you can change your API token. Okay, so it's still going. More questions? Or we can move on and come back. We'll move on and come back. Yeah.
So, as far as I understand, so far we haven't needed TKIT.
You haven't needed it, but it's helped you along quite a lot. Because every time I did a from PyTicket import, I was using Ticket. So, and there are quite a few of those if you look.
Technically, we could have done that with Qiskit or something.
Oh yeah, there's a number of things you can do the similar things with. The Qiskit may not have a function called expectation from counts, but you can find a way to do it with Qiskit. Pretty much everything I've shown you so far, I think you can find a way to do it with Qiskit. But it,
Quality of life functions.
yeah.
But then for that back end, like you can switch it to a non-Qiskit
Yes, you can. Yeah.
with this without changing anything.
Right. That's a good point. Yeah, thanks. Okay, is it done? Please be done. Oh, still going. Right, we'll talk through the rest because it won't let me run any more cells until that one finishes. For this instance, we used, how many did we use? QA calculate. We used 3 layers, I believe. Is that the number? Yeah. But we could instead, there we go. It's done. This looks similar to before, but not as good. So if you look at the correct states, their probability isn't quite as high as before, and all the wrong states have got more probable. And this is pretty much only due to the noisiness of the device that we're simulating, i.e. there's things going wrong with what we're doing, so we're not applying the correct unitaries all the time, so we get more errors. But this is kind of the idea behind variational algorithms, i.e. we can still infer the correct answers even if there is a degree of noise in theory.
The noisy simulation, it's pulling back the noise profile from the actual device.
It is, yeah. So it's using whatever is the latest calibration information that's available. Yeah. So in this case, this is mostly useful for the hackathon, but in this case, it's using the local Qiskit noisy simulation, which uses a fairly simple noise model. The the Quantinuum emulator that we'll have access to on Thursday or Wednesday to Friday, whenever I manage to get everyone's emails in, that uses a proprietary noise model that's quite heavy compute that is meant to be highly tuned to the Quantinuum device. So that produces results that are fairly reliable as to what the device would actually do, whereas this is more qualitative. Right. Okay, so instead of using 3 layers, if we just wanted 1, we can just provide one angle each, and look at that. Obviously, it's a lot shorter than before. It's not very big at all. And we can use that to run the same thing. And this one is only 12 CX circuits. If you're interested in this, how many layers there are, what are we doing, try exercise 4 and try and do better. Right, now we will start finally looking at some specific ticket things. How much have I got left? Ooh, a fair amount. But we've got half an hour, it's fine. Okay, so we will start by compiling our circuit for the device, targeting our circuit for the device in various ways. Starting automatic, and then we'll get deeper and build it ourselves. So let's set up our emulator backend again with Guadalupe, and then for the rest of this, we'll keep using this smaller circuit just so it's easier to see what's going on. It's the same principle, just on more layers. So if you want to use the default compilation, we don't care what the compiler does, we just want it to do something for us and make sure it can run on the device. We use get compiled circuit, and the default optimization level is 1. So like a traditional compiler, there are default optimization levels per backend, so 0, 1, and 2, and the default is 1, so this will just do 1. 1 means do a bit of optimization and make sure it can run on the device. 0 means just make sure it can run on the device, don't optimize it, I know what I'm doing. And 2 means try really hard to optimize it. Spend a bit of time computing if you want to. Right, so let's look at starting one with just default compilation and ask it how many gates there are. The time here is just to retrieve the information from IBM again. So here is our circuit, and we've got 73 gates total and 18 CX gates. The CX gates are our 2-qubit gates. That's the metric we really care about. We want that to be as small as possible. So we know that in our preparation circuits, we're using something called phase gadgets. If you're interested more in what those are, look them up in the papers that we shared, but they're essentially evolutions of under this exponentiation of Pauli's. And we have a special path that is really good at optimizing those, specifically tuned to these kinds of algorithms, these kind of variational algorithms. So we'll prepare our circuit again and just apply that path directly and see what happens. Now, instead of 18, there are only 12 CX gates in the circuit, which is a pretty major win. And the number of total gates is an even greater reduction. And so we're able to do this because we have an understanding of what are the components that go into our circuit, and we know what kind of path is good for that. And in the near term, where we're really hyper-optimizing quantum computing, that kind of knowledge is going to be quite important. Right, so we've got it optimized. Now we've got to make sure it can run on the device, and the most important problem there is the connectivity problem we talked about. We can only use certain edges, certain pairs of qubits for 2-qubit gates. We're going to do something called noise-aware placement. The idea here is that when all the qubits on the device in terms of logic are identical, they all start in the 0 state. So in our circuit, we can map any qubit to any qubit on the device. We have freedom of choice there. So we might as well make choices that minimize the number of swaps we have to put in to make connections. So that's the placement part. And the noise-aware part is we know something about the noisiness of these qubits and the operations we can do on them. Let's use that information to pick the best qubits to put our circuit on. I.e., if our circuit uses fewer qubits than are available on the device, let's try and pick the best ones. So that's what this routine is doing. Yeah.
I didn't understand the order in which these routines are prioritized for the optimization. Things I talk about are one, the picking of qubits that are conveniently connected, and the second is the picking qubits that are little noisy.
Yeah, so it's a heuristic, but we prioritize ones that are conveniently connected because the any swap gates are going to be, so a swap gate is 3 C nodes.
We want to minimize 2-qubit gates.
Exactly, exactly. A swap gate is 3 2-qubit gates, so it's very costly. Okay, so this is something that's actually done behind the scenes for you by the default compilation path. We're just looking in detail at the steps. So we get the noise-aware placement class, and we initialize it with the connectivity of the device. And then we also give it the error information we have about the qubits and the gates. We get our circuit, and then we just ask the placer to suggest a mapping of qubits onto the device. And then these are just some algorithm heuristic configurations that we're going to make convenient choices for. And then we can ask it what choices it's made. So the Q qubits are our qubits from the circuit, and the nodes correspond to actual qubits on the device. So it's made 2 suggestions here, and in this case it's saying put qubit 0 from the circuit on the qubit 10 on the device, and so on. And then we can also use the CX mapping pass, which is what's going to choose these swaps. And it's also going to decompose those swaps in terms of C-naughts and perform any cancellations of C-naughts and optimizations that it can make as it goes. So we prepare our circuit again, and this time we set up the mapping pass with just the connectivity, and we give it, it needs a placer to do the initial placement, so we give it the placer we've already made, and we say that CXs don't have a direction. You can pick C0 of qubit 0 to 1 or C0 of qubits 1 to 0. And then that's a compilation pass like any other, so we can apply it to our circuit and get the stats on that. And the number of gates has gone up, but the number of C0s hasn't. This is not typical. Typically, because you're adding swaps, you'll have to add C0 gates, and this number will usually go up. But in our case, the pass is done really well, and our circuits are not very big, so we end up with the same number, while still satisfying the connectivity of the device. Okay. In TKIT, we also have the concept of predicates. Predicates are essentially properties of the circuit that I can check. So one of them might be, check for me that this circuit only comprises of these gates. Or it might be, check for me that this circuit complies to the connectivity constraint of this device. Or it might be, check for me that all the measurements in the circuit only happen at the end, so I can measure all my qubits together. Things like that. And I might have conveniently mentioned, yes, off the top of my head, all the predicates that are imported here. There are more, but those are the ones I just mentioned. And so each of those is initialized in a different way. So the gate set predicate, you give it the gate set that you are checking for. In our case, this is the gate set of IBM devices, which is also encoded by the backend. The backend does these checks for you to make sure you don't submit circuits that are going to fail. And for each predicate, we can ask it to verify the circuit. And this one is just known circuits in the middle, measurements in the middle of the circuit. And this one is, for this connectivity map, check it only uses those edges. And if we verify those, we get the mid measurement is true, but our base circuit that we defined isn't in the right gate set and doesn't satisfy the connectivity predicate. For the gate set, we can use another convenient utility thing called an auto rebase pass. An auto rebase pass function, you give it the set of gates that you're targeting, and it will generate a pass if it can, based on known decomposition in the library of known transformations. If it knows something about these gates, it will make you a pass that does the transformation to that gate set. So in this case, it does know CX as repeated, which we don't need. And then we can apply that pass directly to our circuit and then now check it again. So if we do that, we now see we meet the predicate, and these are the things we saw earlier. Okay, and then if you ask it TKIT to do optimization level 2, typically what it'll do is run this full p-pole optimized pass. What this corresponds to is basically it's a tailor-made recipe that we've made for running all of our p-pole optimizations in a certain order and in a certain series of steps. You can look at it in the source code if you want to. That we generally performs very well in terms of circuit optimization. It can be quite slow because it can do things like up to 3-qubit state squashing and unitary resynthesis, which is quite expensive. So, but we can, in our case, we can just import that and apply it straight away. And we see that it ran fairly quickly for our case, and it managed to get the CX gates down to just 6. In fact, halving it from our previous best. Okay, and now we can put all of the things we did together, and this is, I think, essentially well, other than this optimized phase gadgets at the start, it's very similar to what will be actually running under the hood in the backend default pass if you choose optimization level 2. But we can choose this meta pass like a sequence operator and just give it a list of passes, and it will construct a pass that in C++ will run all these passes in sequence without having to go back to Python, so it's very high performance. Right, so we're just putting all the passes we talked about already together, get the circuit again and apply it. And even after making sure that it matches our device, we're still left with only 6 2-qubit gates and 52 other gates. There's an exercise here if you're interested. All right, and then only a couple of things left. The compilation unit is a sort of advanced concept that wraps all of these things together in one. Unless you're really into compilation, you probably won't use it, but the idea is essentially you wrap a circuit that you're trying to compile and all the predicates that you want it to satisfy. And then you can check all the predicates on that circuit, apply passes to it, and then check it again. So in this case, we can check before we apply our pass and after, and we see that beforehand it was not good enough, but now the pass that we defined is good enough to satisfy all the constraints of the device. Yeah, go ahead.
What does it mean to compile a circuit, and what is the difference between compiling and transpiling?
Right. The terms are fairly interchangeable. Compiling, the issue is we're trying to steal terminology from classical computing and programming, and then things get confusing. Compiling in normal programming typically means I have some source human readable language, and I have a program that's going to transform it into machine language, right? And then if you say optimizing compiler, it means while it does that transformation, it's also going to try and rewrite so that it's more optimized in some way. It's less resource intensive. That's why we say TKIT is an optimizing compiler for quantum circuits, because we transform a circuit into something else by optimizing. But the TKIT representation of circuits is able to capture both the high level and the low level. So it's not really going between two languages.
Each square in the drawing is a gate that is a physical operation.
It can be, but it can also be high level. So this is like the lowest level circuit, where each square is a physical operation on the device. But if we looked at our top one, with
I meant the case when each square is a base operator of the
right. But we also saw ones like this, where each box is encoding something far higher level and abstract, and you can get more abstract than this. So the representation supports a series of abstractions, and compiling typically means removing abstractions. Transpiling typically means I'm transforming between one level of abstraction and staying at that same level of abstraction, but just rewriting. That's the terminology Qiskit prefer to use, but it's very similar concepts. Right, scroll all the way back. Where were we? Okay, and we could rerun this with our new pass with the calculate, but this one I know to be quite slow. Well, as slow as before, so we won't do it. But basically, because we've got, actually no, let's run it. Let's see what happens, and I'll talk through the other one while it does that. Okay, the final feature we are going to look at is symbolic compilation, I believe. Yes. So the parameters we talked about already, our gammas and betas, get encoded as floating point values in our circuit. They correspond to, they'll end up mapping to, in the device, apply this pulse for this width or this amplitude or something like this. That's what those numbers correspond to. But we could think about this more symbolically and think, I just want to write a circuit where I have a rotation by alpha, and I'll define alpha later, but we can compile alpha, right? So if I had, just using the alpha, so if I had an RZ of alpha followed by an RZ of beta, I can rewrite that in the compiler as just one RZ of alpha plus beta. And in fact, TKIT can do pretty much all of its compilation over these symbols. And for that purpose, we use SymPy symbols, if any of you used SymPy before. And the benefit here is you saw that for any given set circuit, we run it many times with different parameters, right? But the compilation really is the same for each. Most of the time. There are special cases where you get certain parameter values where you can make extra cancellations, where like you happen to end up with 0.5 and minus 0.5 and it disappears or something like this, but those are unlikely. So in general, we can do most of our compilation just symbolically and then just update the parameter values on the compiled circuit. So that's what we're going to do here. We ask for a number of symbols for each of our parameters from SymPy. Oh, this one's still running, isn't it? Yeah. Sorry, no. So this is an example of a symbolic circuit with just A and B, a simple one, not the one we're running. And we can compile that symbolically. This will say false if I could run it. But then we can use this symbol substitution function to say, for this symbol A, set it to the actual concrete value 0.1. And then if we check this no symbols predicate again, it will say all your symbols are now real values and we can run it. Whereas if I'd gone to process circuit with circ symbolic, I would have got you can't run a symbolic circuit, doesn't make any sense. Okay, so in our case, we're just going to redefine some functions. So we get the Hamiltonian as before, the prep circuit. This time, instead of providing values, we provide symbols. And then we do the measurement preparation in the same way and compile symbolically for each circuit. Yep. And then the sim instance, we just do the compilation here when we prepare the circuit. But for a particular set of parameters, this time for a particular instance, we'll pass in some values. We substitute those symbols in here, just take them off the lists and put them into the circuit, and then run them all, get the results as before. And this is a very similar function to before, just making sure that you don't generate the circuit afresh every time. You generate it once and just substitute the symbols. Same as before. And now we can run it with the symbolic calculation, and in theory, because you're compiling way less, you'll get a small speed up. But in our emulator case, the compilation time is so much faster than the simulation time that you probably won't notice it, but if you wanted to check it, you could do exercise 6 to see how much faster it is. Let's see if our previous example has run. It has. And in theory, yeah, so if you now look at the green bars, they are, even though they're running on the same emulator, they're higher than before because we've optimized our circuit such that there is less noise being incurred. That's the main purpose of Ticket, basically, to make your results better. Right. Okay. A review of what we've covered then before I take more questions. We've looked at constructing circuits using Ticket and some helper methods for generating these based on Hamiltonians that you can define mathematically. And then we looked at compiling it, either using default or custom methods to achieve better results, either in terms of actually results from your algorithm or the whole thing running faster. If you're interested in more advanced usages and running in experiments and so on, we will go through those in the joint session, and the exercises that are in here and Callum's warm-up exercises from the more basic stuff earlier, those will be available as well, that you can go through them during the joint instance and ask us questions about those. That is all for now. I will take questions for the remaining time, and if there are not many of those, we can break early. Yeah.
So this QAOA, is there, I mean, I found a lot of text about it, but is there something which is maybe you suggest to go more in depth?
For QAOA, Callum, you might have a please answer this.
So there's the original paper, which
The
is
best text, I mean, that can help me understand better QA.
okay. I think the Cascade textbook, if I'm right, has like an expository like thing on QAOA. I don't know if you've come across the Cascade textbook before. It's quite a good resource for learning about different algorithms. I think they have one on there.
The Qiskit textbook is available on the web for free. Yeah.
So, at least to me, for let's say an example problem, right? This still felt like a lot of code,
Mhm.
and just to solve the max cut problem once for a small problem. So, is what we've done here the highest level of programming that's currently available, or did we go more low level to demonstrate the concepts?
You know, we definitely went quite low level to demonstrate the concepts of what's behind, because Ticket is for we see Ticket as for two kinds of people. One, people who write algorithm libraries. So we have teams in-house that write algorithms libraries that depend on Ticket. So it's a platform for doing that. And two, power users, people who really want to get the maximum out of their quantum experiments. They have limited device time. They would need to get a paper out and for it to be as good as possible. And the people who really understand the problems, and those people might write this much code. I mean, here we did lots of things multiple times, so it looks even bigger than it is. But there are, so I believe QAOA is one of the algorithms available from the Qiskit algorithms section, and that's more high level. You can just provide the initial parameters and it'll just do this in the background, but maybe not as optimally as you can do. For example, our chemistry package is aimed at chemists in industry who are used to using classical codes for chemistry. So that's very high level. It's like define a molecule, and then we will take care of the rest and find its energy for you from a quantum computer, or do some dynamics or things like that. Yeah. And that'll run all of this stuff in the background. Yeah. All right. Shall we take leg stretching, I think it's called in the thing? Stretch some legs?
Thank you.
No worries.
The next session is here or
Upstairs.
will we take?
Yes, bring your laptops.
Thank you very much.
Right, I will now disconnect and then go change my API key.